Good afternoon, everyone. So we are the Guardian, and sorry, there is some delay for the PowerPoint. Here is our development team, and I'm Wei Yun.
I'm Lexus. I'm Jiajun.
I'm Ning.
We aim to use the autonomous drone system to solve the elephant-human conflict. And this kind of conflict is very prevalent in the worldwide because nearly 20% of the human population live in or near the elephant habitat. And over the 100 years, the number of African elephants decreased for more than 90%. And the cooperating is one of the major forms of the conflict. According to the WWF, World Wildlife Fund, about 65% of the crop destroyed are wheat and 21% of the crops destroyed are sugar canes. And these two kinds of crops are the major source of income for small plantations. Up to 600 pounds of food can be eaten by a single elephant per night. And this means a lot to a small household. And that also causes a lot of damage to large plantations because, for example, in Rio, the largest oil producing province in Indonesia, about $100 million are lost by cooperating each year. And in India, according to the national report, up to 300 humans and 50 elephants are killed during cooperating each year. And according to the National Geographic Channel, the elephant range, about 500 people are killed by elephant each year in the world. And this photo is taken in Rio, the largest oil producing province in Indonesia. You can see in the photo that the elephants are destroying the crops and wasting millions of dollars.
So this is the basic flowchart of our solution for the elephant-human conflict. Basically, we utilize the fact that the elephant is afraid of drone noises and it can be used to scare them away. And so the first step, we'll try to place a GPS tag on the elephant by tranquilizing it. We will then probably put a bracelet on the elephant's ankle, or maybe we'll just strap a GPS tag onto the elephant's neck. And then a ground base is set up in the place where the protection of the crops are needed. The ground base will emit signals which the GPS tag will be able to pick up when a signal is strong enough. So the range of the signal from the ground base basically defines the perimeter of the protected area we want to prevent elephants from entering. And the next step will be when the elephant with a GPS tag going to the range of the signal of the ground base. So when the signal is strong enough, the GPX is woken up from sleep mode and start to send out real-time GPS coordinates. And the third step is when the drone receives these coordinates and fly to the coordinate of the elephant. And next step will be when the drone is about to reach the elephant coordinate, the onboard camera is turned on and the footage is then analyzed with AI algorithm loaded on NVIDIA Jetson Nano to identify and track the elephants effectively. The final step is since the elephant's afraid of drone noises, they will be able to chase the elephant away from the ground base and effectively prevent the elephant from damaging the crops. And okay, so this is a visualization of the process we proposed. The yellow shaded circle represents a region of the signal covered by the ground station. And, the ground station is represented by the three little houses in the middle of the circle. So the yellow shaded circle is the region where the signal from the station will trigger and wake up the GPS tag on the elephant. So as you can see right now, the elephant is outside the yellow region, which is the protected region we want to prevent elephants from entering. And right now, since the elephant is outside of this region, the drone is still on the ground. And when the elephant comes into the protected region around the ground base, the XP module receives signal from the ground base, which triggers and wake up the GPS tag on the elephant. And then the GPS coordinates of the elephant is sent out by the XP module on the GPS tag and is then received by the XP module on the drone. The drone will then take off. And the drone will then use waypoint navigation to fly to the coordinate of the elephant and try to scare away the elephant. And when the drone is close enough to the position of the elephant, the onboard camera will turn on. And finally, the onboard Jetson Nano, which is running the AI algorithm, will try to pinpoint and track the elephant's movement using the footage captured by the camera. And this will ensure the drone is chasing away the elephant in the right direction. And then the drone will try to maneuver until the elephants are outside the protected area.
So this is the system block diagram of our whole design. The drone comes with two main parts, the onboard computer Jetson Nano and the DJI N3 Flight Controller. The Jetson Nano runs the object detection and tracking program with the camera connected, and it sends the flight control commands through UART to USB connection to the N3 Flight Controller. The flight controller then sends signal to the motors to control the drone. A power system is providing power for both of them. There are 3 XP modules, one in the ground base, one on the drone, and one on the GPS tag. A battery provides the power for the microcontroller to control the GPS module.
So right now I'm going to walk you through the schematic of our GPS tag. On the left-hand side here, you can see a sketch for our schematic in the Eagle. And on the top right here, it's a high-level block diagram for our GPS tag. And over here, we have the Arduino microcontroller. And this corresponds to the XP module that is responsible for the communication, sending out the GPS signals. And this one is the GPS module that's responsible for locating the elephants. The SD card here is used to store the coordinates of the elephant for future research. And this is our PCB layout. So we use the 4-layer board, and the size of this PCB is very small, and it's also very light. So if we install the GPS tag on the elephant will not notice it. And according to our estimation, the GPS tag can last for about 200 days. And it's calculated based on the storage of our battery and the power consumption of our components. And in fact, we use two kind of power system for our GPS tag. One is the backup battery for the GPS module, and then we also use a LiPo battery to power the whole system. Here is our assembled PCB for the GPS tag, and you can see it features the SD card, the GPS, ZigBee, and the Arduino microcontroller.
So for the drone part, we use Terra 680 Pro frame that comes with the motors and ESC, electronic speed control. Jetson Nano is the onboard processor to run the object detection and tracking autopilot program. DJI N3 Flight Controller controls the drone to perform flight actions. And we use a camera for object detection and tracking, and XB to receive the GPS location from the GPS tag. And the 6S battery provides a 20 minutes of flight time and a range of 4 miles.
Okay, so we use Jetson Nano as our onboard processor on the drone. We choose this for computer vision since it has a decent NVIDIA GPU, which is great to speed up the neural network detector we're using. It also has a low power consumption, so we can extend battery life for our drone. However, turns out Nano is still really constrained in terms of its compute. So it's still challenging to get our tracking algorithm to run in real time on this hardware. So we combine neural network with a lot of the other efficient techniques to get it to work. And I'll come back to that later.
So we choose DJI N3 as our flight controller, mainly because of its stability. It has two IMUs providing dual IMU redundancy, making the drone much less likely to fail to operate and crash. It comes with a GNSS compass and onboard GPS to give us the direction and GPS location of the drone. A built-in power management unit, PMU, provides the power supply. The end pins are used to control the motors, an API port with the UART connection to receive the instructions from the Jetson Nano, and the DJI Onboard SDK are used to speed up the programming part. The DJI Onboard SDK is installed in Jetson Nano, and it is the interface for DJI N3, providing functionalities such as flight actions and aircraft state data retrieval. For example, it can make monitor landing and takeoff, perform roll your pitch to adjust the attitude, get data like direction, GPS, and altitude. These are essential for developing the autopilot program to herd the elephants away.
Okay, now I'm going to break down our software stack. So our software architecture is split into two parts: visual tracking and drone control. Tracking is written in Python to work with a lot of the machine learning libraries, and our control is written in C++ so that we can use DJI SDK and be flexible in low-level interfacing. When we launch our control program, we will spawn the tracking program as a separate process and communicate with this through a socket. The tracking program will send the bounding box around the elephant to the control program at each frame. And then the control program will run PID control on the bounding boxes. The control algorithm uses the area and the centroid of the bounding box to control the drone. Okay, and that brings me to how our tracking algorithm works. Common filter is a great algorithm to model the motion of objects, so we use that to keep the tracking smooth. Bounding box position and velocity encoded in the state of the Kalman filter. Optical flow takes 2 frames, an old frame and new frame. After it matches the object from the old frame, it will output a new set of tracks. And these tracks are used as a measurement to update Kalman filter. Kalman filter will then output a new state, which has all the bounding box information for the new frame. We also run a CNN detector every 5 frames to detect new elephants. So the detector takes the current frame, outputs a bunch of detections, and we associate each elephant detection to each track in the old frame. If we associate detection to a track with high certainty, we can just keep tracking it. But if we can associate detection, we'll just create a new track for that object. And again, we use the final output tracks to update Kalman filter. Because we will only run the detector every 5 frames, so we can actually get everything to run at 32 frames on average, which is already in real time. That's pretty nice. So how do we actually transfer the bounding boxes into our control signal, for the drone? As you can see, the green box in the image is the bounding box output by our visual tracking. It's basically the feedback signal we use for control. The blue box is our reference bounding box, which means we want the green box to be as close to it as possible. The red arrows are the control arrows. The arrow in the middle, the other X and the other Y, shows the difference between the centroid of the green box and the centroid of the entire video frame. The arrows at the 4 corners, the other A, shows the difference between the area of the green box and the blue box. We pretty much fix the throttle of the drone to keep it at the same height. We use the other X, the horizontal difference, to control the yaw and roll of the drone. We use the other Y, the vertical difference, to control the pitch. The other A also controls the pitch since it roughly reflects the distance to the elephant. So we want to move the drone forward or backward based on that.
Okay, so this is our demo video this is a simulation. So we didn't include anything related to GPS waypoint navigation because it is basically a building function of the DJI SDK. So basically we are simulating the tracking movement of the drone. The position of the elephant is approximated by the center of the rectangular box generated by the AI algorithm, which is what Alexis talked about. So in the simulation, we basically have the drone moving in the same direction as the elephant in the footage. And as you can see, there's a coordinate system in the middle of the screen, and it's showing the drone flying past in the simulation. Okay, so let's play the video. So the first clip basically shows the animal moving towards the upper right. And as you can see, the drone is basically replicating that movement in this simulation, essentially tracking the elephant. And the second clip is the elephant moving towards the right, and the drone is also moving towards the right to track it. And the last clip will be basically the same thing, the only difference being that the elephant is now moving towards the left.
So we would like to thank Professor Yoga and Professor Schultz, Adi and Kyle for their very insightful technical discussions. And that's it for our presentation. Any questions?
So based on your experience with this project, would you make any changes when deploying this in like actual regions that have elephant-human conflict?
There are some like actual like projects that's already like deployed in Africa. So very similar to ours, but I think our like, you know, a combination of like GPS and, you know, visual tracking system will like do this job more effective than those like existing systems. So they are already applied in some sense.
And we do think that our project can scale. We can like improve our project to make multiple drones coordinate at the same time to like herding like a larger area for elephants to herd them away.
So was drones the ultimate solution to this problem? Did you guys also consider networks, sensor networks, like a mesh network of deployed sensors or speakers? And why did you then settle on using drones instead?
One problem with the installed speakers is that sometimes if you deploy it in Africa or in some remote places, they will be stolen easily. So if you use drone in the air, no one can steal it.